This is the video for Accelerated Geometry on Section 11-1 and 11-2, Finding All Roots of a Polynomial Equation. Key vocabulary is multiplicity. Essential question is, how do you identify the multiplicity of roots, and how do you use the rational root theorem and irrational root theorem to solve polynomial equations? The fundamental theorem of algebra states that every polynomial function of degree n greater than or equal to 1 has at least one zero, where a zero may be a complex number. Corollary to that theorem says that every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities. So for example, if the degree of a function is x to the 6, so you have a degree of 6, then you're going to have 6 zeros. Now you may not necessarily see the zeros on the graph because of the complex number solutions. The multiplicity of a root r is the number of times that x minus r is a factor of p of x. When a real root has an even multiplicity, the graph touches the x-axis but does not cross it. So if we look at the graph that I have over here, you will notice that at 3, the graph touches the x-axis but does not actually cross it. So we know that this has to have an even multiplicity. When a real root has an odd multiplicity greater than 1, then the graph bends as it crosses the x-axis. So if you look at this example at 5, you can see how the graph is bending as it's crossing the x-axis. So I know this has to be an odd degree greater than 1. Now what happens if it is 1? Well, then the graph just goes through the x-axis. So like right here at 1, the graph goes straight through it. So I know this has to have a degree of 1. Now you can't always determine the multiplicity of a root from the graph. So for example, I have no idea what each of these degrees are except for this first one. I know that's a degree of 1. This one, it could be a square, it could be a fourth, it could be a sixth. We don't know. And this one, it can be any odd degree that's greater than 1. We don't know the exact number. To determine, we can look at the factored form of the polynomial. So in our first set of examples, it says find all zeros by factoring. So first thing I'm going to do when I factor this is greatest common factor. In this case, it is 4x to the fourth, which leaves me with x squared plus x minus 6. X squared plus x minus 6 can be factored further to x plus 3 and x minus 2. So if I look at this, I can see that I'm going to have a 0. If you set this equal to 0, you're just going to get x equals 0. So we have a 0 of 0, but the multiplicity is 4 because the degree there is 4. X plus 3 equals 0 tells me that x equals negative 3 with a multiplicity of 1. And x minus 2 equals 0 tells me that 2 is a 0 with a multiplicity of 1. And we can verify that by looking at the graph, because at negative 3 it goes straight through it, so I know that's a degree or a multiplicity of 1. At 2 it goes straight through it, so that is a multiplicity of 1. And at 0 it touches it but does not actually cross the x-axis, so that tells me it has to have an even degree, and in this case that even degree is 4. Next example, first have to have it equal to 0. And then I'm going to factor by grouping on this one because there's 4 terms. So I'm going to group the first 2 and group the last 2. Common factor here is x squared. That leaves me with x minus 2. Common factor here is negative 25. That leaves me with x minus 2. So this factors to x squared minus 25 times x minus 2. X squared minus 25 is the difference of squares, so that's x plus 5 times x minus 5 times x minus 2. And this can't be factored any further. So this tells me that my zeros are -5, +5, and +2, and all have a multiplicity of 1. And I have 1, 2, 3 zeros, all multiplicity of 1, and indeed my highest degree was 3. The next set of examples is pretty much the same thing, it's just worded a little differently. So it says identify the roots of each equation and state the multiplicity of each root. So I'm going to try to factor this, and first thing I can do is pull out an x. Then I'm going to, there's 4 terms left inside here. I'm going to try and factor by grouping. Here I can pull out x squared. That leaves me with x minus 8. I can pull out a 4. That leaves me with x minus 8. So that factors to x times x squared plus 4 times x minus 8. So I can see that I have a 0 of 0 and a 0 of 8, but I need to keep finishing solving this one. So I have x squared plus 4 equals 0. So x squared equals -4. So x equals plus or minus the square root of -4, which if we remember from last semester, that tells me that x equals plus or minus 2i. So my zeros are 0, 8, 2i, and -2i, or you can just write plus or minus 2i. And all have a multiplicity of 1. One more. So greatest common factor here would be 2x to the third. That leaves me with x to the third plus 3x squared plus 12x plus 36 . There's 4 terms inside here, so I'm going to try factoring by grouping. So I have 2x to the third. Common here is x squared. That leaves me with x plus 3. Can pull out a 12 from this one, so that leaves me with x plus 3. So I have 2x to the third times x squared plus 12 times x plus 3. So I see I have a 0 with a multiplicity of 3. I see I have -3 with a multiplicity of 1. But I need to finish solving this one. So I have x squared plus 12 equals 0. So x squared equals -12. So x equals plus or minus square root of -12, which is plus or minus 2i radical 3. So then I have 2i radical 3 with a multiplicity of 1 and -2i radical 3 with a multiplicity of 1. Rational root theorem. This will make more sense to us when we start working problems here in just a second. But when I'm referring to this, the p is the factors of your constant term, and the q is the factor of your leading coefficient. All of our possible roots are going to be p over q. The irrational root theorem states that if, for example, I tell you that 2 plus radical 5 is a root, then 2 minus radical 5 is also a root. These come in pairs. You can't have one without having the other. Same thing with the complex conjugate root theorem. So it says if a plus bi is a root, then a minus bi also has to be a root. So if I tell you that 3 plus 2i is a root, then you should also know that 3 minus 2i is a root. Or if I tell you that 4i is a root, then negative 4i is a root, and vice versa. In these examples, it says to state all possible rational roots for the polynomial, then use a graph, synthetic division, and factoring to find all the roots of the polynomial. So first thing we're going to do is find all the possibles. So I'm going to list out all the factors of p. Remember, p comes from the constant term. So the factors of 4 would be plus or minus 1, plus or minus 2, plus or minus 4. Your factors of q come from your leading coefficient. So in this case, it's just 1. All of your possible come from doing p over q. So we have 1 over 1, which is just 1, 2 over 1, which is just 2, and 4 over 1, which is just 4. So these are all of our possible. Next thing it says is to use a graph. So in your graphing calculator, graph the polynomial. So the graph that you should have from your calculator should look something similar to this. And what you're going to do is you're going to look at the graph and you're going to use your second trace button and then option number 2 that says find the zeros. And you're going to find one of these zeros where you see where it crosses the x-axis that is one of these numbers. So if you calculate the one that's right here, you will get the negative 2. And then you're going to use synthetic division. So we have negative 2. Our coefficients are 1, 1, negative 4, and negative 4. So that's a 1, negative 2, negative 1, 2, negative 2, 4, and 0. And you should get a remainder of 0 because we already verified that it was a 0. So if I started with x to the third, this is now x squared. So really that's x squared minus x minus 2. And we can finish factoring that because that factors to x minus 2 and x plus 1. So now you can see all of your zeros or all of your roots. You have the negative 2 that you did on your graphing calculator. And then you have a positive 2 here because that's going to tell you x is 2. And a negative 1. Let's try another one. So first thing we're going to do is list out all of the factors of our constant. So that's 1, 3, 5, and 15. Q would be all the factors of your leading coefficient. So that's a 1, a 2, and 4. So all of our possible roots is going to be 1 over 1, which is just 1, 1 over 2, 1 over 4, 3 over 1, which is just 3, 3 over 2, and 3 over 4. Then you have 5 over 1, which is just 5, 5 over 2, 5 over 4, 15 over 1 is just 15, 15 over 2, and 15 over 4. Next, I'm going to graph the function. So when you graph your function, it'll look something like this. So when I start calculating these zeros, the first one that I calculate would be this one right here, which is at -3. So I'm going to use synthetic division. My coefficients are 4, 10, 4, 25, and -15. Gives me -12, -2, 6, 10, -30, -5, 15, and 0. So I had x to the fourth from the beginning, so this is now x to the third. And I don't like dealing or trying to factor things with x to the third, so if I don't have to, I'm not going to. What I can do is see if there's another one of these rational roots that I can find on my graphing calculator, which would be this one, and I can find out that that is 1/2. So I can continue. I'm going to use 1/2, but now my coefficients here are going to be what I ended with on the previous one. So I'm going to have the 4, -2, 10, and -5. So carry down my 4. That's going to be 2, 0, 0, 10, 5, 0. So now this is x squared. So that just tells me I'm dealing with 4x squared plus 10 equals 0. And I can solve that. That gives me 4x squared equals -10. So x squared equals -10 over 4. And yes, this can be reduced. However, if you notice, you're going to take the square root, and 4 is a perfect square, so I'm going to leave it like it is. So when I take the square root, I get plus or minus the square root of -10 over square root of 4 is 2. So that's just x equals plus or minus I radical 10 over 2. So all of my roots start from the beginning. We have the -3. We have the 1/2. We have I radical 10 over 2 and -I radical 10 over 2. Let's try one more of these. So listing out my factors of p would be plus or minus 1, plus or minus 2. My factors of q, which is the leading coefficient, would be plus or minus 1, plus or minus 2. So my possible zeros, 1 over 1 is just plus or minus 1, plus or minus 1/2, plus or minus 2, and 2 over 2 is just 1. We already have that listed, so we don't have to list it again. So now I'm going to graph this. When we graph it, our graph will look something like this. So we can start off with finding one of these zeros to see which ones come out to be this. The first one that I see is right here, and when I actually calculate it, it comes out to be -1/2. So if I use that in synthetic division, your coefficients are 2, -5, 1, and 2. That's going to give me -1, -6, 3, 4, -2, and 0. So since I started with x to the third, this is now x squared. So really that's just 2x squared minus 6x plus 4. And I can factor that. First thing I notice is they're all divisible by 2. And then this factors to a minus 2 and a minus 1. So this one tells me that x is 2, and this one tells me that x is 1. So my answer to all the roots would be the -1/2, 2, and 1. Last set of examples. We're writing the polynomial of the least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. Okay, so first thing we're going to do is if I know that x has to equal -2 for it to be a 0, then solve this backwards. That tells me that x plus 2 is the factor. So our three factors here are x plus 2, x plus 1, and x minus 1. And now we're just going to multiply these out. So the first set of parentheses would be x squared plus 3x plus 2. And then if I did this vertically, gives me -2, -3x, -x squared, 2x, 3x squared, and x to the third. So my answer would be x to the third plus 2x squared plus x minus 2. And I just realized that would actually be minus x minus 2. So my answer here, first things first, do I have rational coefficients? Yes. Is the leading coefficient a 1? Yes. So then my answer would be f of x equals x to the third plus 2x squared minus x minus 2. Number 9, we have the zeros of 0, 2/3, and 3. So I know my first one, if I'm just saying x equals 0, that just tells you that your factor is x. For your second one, if you have x equals 2/3, work that backwards. So opposite of dividing by 3 would be multiplying by 3, and the opposite of adding 2 would be subtracting 2. So that tells you that 3x minus 2 is the second factor, and the 3 tells me that x minus 3 is the third factor. So distribute this, that gives me 3x squared minus 2x times x minus 3. Boil this together, so that's going to give me 3x to the third minus 9x squared minus 2x squared plus 6. So that gives me 3x to the third minus 11x squared plus 6x, sorry, because you have -2x times 3, so it's 6x. Next thing, the direction said with a leading coefficient of 1. So before we say this is our final answer, here we have a leading coefficient of 3, which means we need to divide everything by 3 to get a leading coefficient of 1. So divide this by 3, this by 3, this by 3. So our answer would be f of x equals x to the third minus 11/3 x squared plus 2x. Last example, we know that we have x minus 1 as a factor, x minus 5 as a factor. Now, remember what I said earlier about the complex conjugate theorem. If -2i is a factor, is a 0, then 2i has to also be a 0. So you can kind of think of this as saying that x was equal to plus or minus 2i. Well, in order to get plus or minus, that means at some point you took the square root. So at the same time, 2i, if you put it back under the radical, would be -4. So the opposite of taking the square root would be squaring both sides and then add the 4 back over. So our last here would be x squared plus 4. FOIL these together. So that's going to give me x squared minus 6x plus 5 And off to the side, I'm going to multiply them out. So that gives me 20 minus 24x, 4x squared, 5x squared, minus 6x to the third, and x to the fourth. So I get x to the fourth minus 6x to the third plus 9x squared minus 24x plus 20. So before I say this is our final answer, is my leading coefficient 1? And the answer to that is yes. So I have f of x equals x to the fourth minus 6x to the third plus 9x squared minus 24x plus 20. And you're finished.